All right, welcome to the last session of today. I'll talk about Spark. My name is Nitschinger. If you haven't been to my RX Java session before, I work as a software engineer on the SDK team, mainly responsible for everything that's JVM related. And since Spark is running on the JVM, I also wrote our Spark connector, which I'm going to talk about here today. Who has no clue what Spark is? OK, yeah. So for those, no worries. We'll actually have two sessions, one today and one tomorrow from a colleague from Databricks, who is going to talk about Spark as well from like a more Spark-oriented perspective. Here we're going to cover it more from a Couchbase perspective. But nevertheless, I'll quickly talk about what is Spark, right? So if you want to summarize it in one statement, Spark is a fast and general engine for large-scale data processing. And while many people use it to get rid of Hadoop to a degree, I see it in a little different spectrum, right? I see it more as a real-time processing engine, or a near real-time, or soft real-time, however you want to call it. And we'll see a little bit later why or what the main reason for that is. Right? So Spark comes is basically packaged as a core component with some other libraries stacked on top, and it's fast. Right, so it's they made some great I would say great implementations, and they had some great programming model and so forth. So they beat especially Hadoop in number crunching quite a lot. And interestingly, it got lots and lots of momentum in the last year or 1.5 years. It's a very active big data project, especially in the Apache community. You can see that, and while this isn't a reliable metric, of course, the Google Trends, what I wanted to show is basically you can see that the interest is huge right now. There's lots and lots of interest in Spark. And also with over like 450, I think it's now even more contributors, there is also lots going on inside the code base as well. They're pushing out releases on a regular basis. So lots of traction going on there. The ecosystem is growing fast. So it's not only about Hadoop. So while Hadoop support is great, but it's also about RDBMS integration, of course, NoSQL integration. There are many other vendors and applications that are certified with Spark. And of course, the Databricks company, they try to certify more and more applications and vendors to make sure the ecosystem is basically in a reliable fashion. And what Databricks also created was something called sparkpackages.org. So you can go there. It's like a central package repository for all Spark modules. Our Spark connector is also published there. It's currently in the second developer preview form. And it makes it easy to find packages and also use them in Spark. So if you're using the Spark command line utility, you can basically pull in packages from there just with a command line and include them in your class path and then just type ahead and do your queries at runtime. Now, of course, they have connectors there, but also other utility libraries which you can pull in as well to make the life easier when you're working with Spark. So if we break the whole Spark thing up a little bit, the foundational piece is what I call here like the Spark core, right? The foundation circles around what they call RDDs, resilient distributed data sets. So this is really the core concept of Spark. Everything circles around those RDDs. And in essence, what they actually are is a collection of data spread across the cluster transparently to you, and they are resilient, which means that if you're running your computations on a cluster and the node fails, Spark is able to restart from a specific point and redo the computations for you, right, in a very efficient way. And the core part here also handles clustering and execution. So when you're writing a Spark application, you don't need to care about if it's running on a 10-node, 50, or 100-node cluster. You basically you program, you do your operations on your RDDs, and then the RDDs will be executed on the cluster. Very similar to how Couchbase works, right? Because you write your Couchbase application, and you don't care if you run against a 5, 10, or 50-node cluster with Couchbase, where your services are, and so forth. That's basically an operational concern, not a concern during development time. And Spark is very similar in that fashion. And on top of the core library, we have lots of utility things or extensions which are very powerful. The first one is Spark SQL. And Spark SQL has a concept called DataFrames. And DataFrames are like RDDs combined with a schema, right? And if you have a schema, you can run SQL queries on top of them. Now, as you could probably guess, Spark SQL and DataFrames, they fit very nicely with Nickel. As we'll see in a bit, actually, our Spark SQL integration is great because we're providing a superset of what Spark SQL provides. And we can push predicates and everything right down into the Nickel query engine. So you're saving lots of network traffic, and we can optimize the path. And again, everything is distributed. So in Spark, while it's running on many, many nodes, that is abstracted away from you. You don't need to care about where those tasks actually executed. You just do your queries and you get a response. Another component is called Spark Streaming. And you can use Spark Streaming to build fault-tolerant streaming applications. So for example, you can fetch data from a Twitter stream. I actually have an example later where we're pulling data out of Twitter and storing them in Couchbase with like a few lines of code. So our connector also provides streaming support through our database change protocol, TCP, so you can actually feed mutations from the cluster into Spark and then do some analysis on them in near real time. Another component is called mlib, which is machine learning. And this is, I think, really interesting, especially if you're doing lots of number crunching and machine learning, because it ships with machine learning algorithms which are optimized for distributed computation out of the box, right? You still need to configure it properly, so you need to know how those algorithms work. But all the context of getting data from node A, getting it from node B, and then doing your aggregations and so forth, this is all handled done by the mlib component. So machine learning gets, on a large scale, much easier with Spark. And the last one is GraphX, which is basically graph computation in a parallel way. So you can also do complex graph traversing and so forth with Spark on your distributed system, basically. So how does it work from a very high-level perspective? I've also put the original paper on here, so if you want to read about those RDDs, the resilient distributed data types, there is this paper from 2012, which was basically the start of the Spark project, right? As very often, open source projects, they start from a paper which was published and so forth. So if you want to read that, I think it's a great introduction into the more formal concepts. Now, how does that work when you're writing an actual application? So you're working with your RDDs, and very similar to what we have with RxJava, right? You have filter and map and all those operations you can apply to your RDDs, and eventually it will look like this. You will have a graph of RDDs which have parents, right? So you have your input here, and then you do a join, and you join two RDDs into one, and then you perform other operations like group by or filter, and you will end up with a structure like this. And what Spark is then doing, it's building a directed acyclic graph out of that, which looks like this. And at this point, it's basically starting to decouple your application logic, and it's trying to figure out where to execute those parts. So it has this scheduler here where it splits up the graph into stages of tasks because it tries to optimize where it's putting those tasks on the workers. There is an operation called shuffle in Spark, which means basically moving data around over the network. And what you want is you want to avoid shuffling as much as possible. Because every time you move data from node A to node B, you need to traverse the network, and it's getting slower, especially for large data sizes. So Spark tries its best to execute as much operations as possible on the same nodes to avoid the shuffling. And then once it creates those stages of tasks, it submits those, right? So, and then those tasks get executed on the cluster. And Spark provides support for example, to run on Mesos, but you can also run it on Yarn if you already have a Hadoop system up and running. So you can see that basically your programming model here is completely abstracted from where it's actually running those tasks. So you can write the application in your IDE. You can try it locally with a local simulator, and then you package it up, and then you submit this as a job to your Spark cluster, and it's just running there. And then, of course, all those tasks get moved onto a worker, and the worker then executes the tasks and performs the computations for you. And the important part here is that the scheduler is agnostic to operators, so it actually doesn't even know what's going on here. And on the other hand, the operations part doesn't know about the stages that are computed. So it's really trying to split up the concerns, and it's gradually going from the programming model back down to the lowest level where the tasks are actually executed on the workers. One more thing. Of course, I forgot to mention that if a task fails on a worker because, for example, the node goes down, because it knows the hierarchy here, Spark can very efficiently recompute only those stages which have failed, which means that if you do large-scale computations, you end up only recomputing partial sub-results of the whole thing instead of redoing the whole thing, right? Which, of course, makes it more resilient and gives you better performance. Now, that's nice, but why should you care, right? What are the benefits of Spark? The first thing is that it's linearly scalable up to thousands of nodes, right? I don't know if we need that much, but the main idea is that if you have more data to process, you can reuse your same code. You just add more nodes into the cluster, and it distributes your tasks across the workers, and you get more efficient processing. In my opinion, it's much simpler to use than Hadoop MapReduce, right? Hadoop MapReduce tends to have really a lot of code, and if you look at Spark code in comparison, it's really tight because it's using a functional approach with all those map and filter and grouping and joining and so forth. To me, it feels like a more declarative fashion to define those operations that you want to perform. And as I mentioned before, the partial recompute on failure really helps you if you have node failures, but you still want to get your computations done. Which is even more important with Spark streaming, for example. You know that like you are consuming data from a streaming source, and you want to keep processing the data 24/7, even if you have node failures and so forth. You don't want to let everything grind to a halt only because one worker did fail. And it really provides an intersection between developers and data scientists because it has an approachable API, and they even provide a Python API. So for people who are just data scientists and are not really like Java or Scala programmers, it still provides an approachable API to them. It has machine learning built in, and I think in the next version 1.4 they even provide R integration, right? So you can interact with R code as well. And even if Hadoop is not mandatory, so you can use Spark with Couchbase, for example, and don't care about Hadoop at all. It originated out of the Hadoop context, right? Because there were some shortcomings with Hadoop, and they motivated the original authors to do something else. So even if it's not mandatory, the integration is very, very tight with Hadoop. So the big difference to Hadoop, I would say, other than how you program your tasks, is that Spark is a memory bound, while Hadoop is mainly HDFS bound. And this is, I think, the main reason as well why computation is so much faster. You can explicitly say, during your stages, you want to persist your partial computations to disk, for example, because you don't want to lose it if you have node failures, right? But it's up to you. If you start with disk-bound operations like HDFS and everything needs to go to disk, of course, your operations get much slower. And it's fully compatible with Hadoop input-output, so you can create RDDs from Hadoop from HDFS files. You can write your computation results into HDFS. So everything that you already have with HDFS and from the Hadoop ecosystem, you can reuse. It's easier to develop because, personally, I find the functional composition approach much easier than doing your iterative MapReduce style operations. And of course, just because of its age, the Hadoop ecosystem is much larger, right? But Spark is catching up really fast. So there is a good chance that what you need out there, what you need in your application is already out there and available as a plugin or as part of the Spark ecosystem. So where personally I see Spark as really as a great tool is like the component between all different other systems, right? So you can use Spark, for example, to read data out of a web stream and write it down into Couchbase. Or you can use it to read data out of Hadoop and write it into an RDBMS and so forth. And because Spark provides great abstractions, it's really like a Swiss Army knife for data operations, right? Reading data out of here, writing data in here. And I have an example as well where we are actually, with Spark SQL, we are grabbing data out of Couchbase and grabbing data out of an HDFS file and then applying a Spark SQL statement to both data sets, right? So you can perform queries on your data, which is loaded into Spark, that it's coming from different data sources, which is very powerful if you want to do data analysis. And another thing which I find interesting is infrastructure consolidation if you combine it with Couchbase. So because Couchbase acts both like as a cache, you can use it to firehose your data into Couchbase, but also like as a real database where you can do everything you want and you have persistence and replication and so forth. You can very easily end up with a system like this. You serve your OLTP applications from Couchbase, but you also feed your real-time streaming data into Couchbase. And then you perform your analysis of the data inside Spark, and then you write the results back into Couchbase, and then, for example, serve it back into your web application, right? So because Spark also provides both the batching approach and the real-time approach, and Couchbase is good for fast data, so feeding data into Couchbase, also storing it in a larger fashion, I think ending up here is something really, really, really appealing, especially if you're coming from a greenfield, if you're planning a greenfield application, right? If you already have lots of systems in place, you can still benefit from merging all those data sources together and analyzing your data in a real nice fashion. So that was basically a general introduction into Spark, but now let's talk about the Spark connector itself. So the Spark connector, as the components in Spark are, is split up into different parts. So for the Spark core, the Spark foundation, what we provide is automatic cluster and resource management, which means that if you submit a task into Spark, of course it's distributing the task to all of the workers. But for us, it means that we need to open Couchbase connections on every worker to the cluster, of course, to make it able to talk to the nodes. So one of the main responsibilities of the connector is to handle the connection management properly for you transparently. As you'll see in a bit, all you have to say is, I want to get data from my travel sample bucket, and then the connector will make sure to open connections on the workers where it needs them, and then afterwards close them when they are not needed anymore. Now then, of course, that would be useless if we cannot create or persist RDDs. So you can use Couchbase both as a data source, so you can create RDDs out of Couchbase data, and you can use it to persist your RDDs, because at some point when you compute your results, you need to put them somewhere, right? So you can put them into HDFS, but you can also, with the connector, put them back into Couchbase. And what we are planning, it's currently not in the developer preview, but what we are planning before GA is Spark itself provides you a Java API as well. It's written in Scala, but it provides you a Java API as well. And we are going to add that for all APIs that the Couchbase connector supports. We are going to add Java API support as well before the GA release. Now, when it comes to Spark SQL, it's really all about easy JSON handling and querying. So we provide two stages. We allow you to send in a raw nickel query, and you get the rows back as an RDD. But if the next step is to integrate with the data frames, right? So what we can do for you is we can actually, you pass in a nickel or a Spark SQL query, we are translating it into a nickel query under the covers, and then we are creating those data frames for you, including a schema. And we even do schema inference for you. So as we'll see in a bit, you can actually, on the travel sample, you can say, I want to create a data frame for airlines, and then you can say print schema, and it will print you all the fields. And we're doing that by fetching documents from the cluster based on a predicate, and then analyzing the schema and then returning that to you. While it's not 100% correct most of the times, because JSON documents can have different structure, very often it's good enough for your data analysis tasks, right? It doesn't have to be 100% perfect all the time. And of course, you can provide a manual schema as well if you want to. Now, in DB2, we have, I would say, partial support. It's already pretty good, but there are still some pieces here and there we need to extend to make it fully Spark SQL GA-proof and remove all the bugs that we found already. And then there is the Spark streaming component, where Spark has a concept called D-streams, which are like RDDs, but on a timeline. So you imagine you get a data stream, and what Spark will do is you can say, like, I want to batch the data up into 5-second intervals. So it will give you the data that's incoming in 5-second intervals, and then you can react to them, and you can slice them up in the way you want to. And what the Couchbase connector provides is a DCP source, which means that it will act as a D-stream source for the mutations that are happening on the server. So if you insert a document, you will get a notification on the D-stream saying, oh, actually, a document has been inserted, right? Which means that you can perform like soft real-time analysis on the data that's incoming, right? Imagine you are storing logs in Couchbase, and then you do some log analysis in Spark streaming as the logs arrive, right? So the current version is 1.0 DB2. So we shipped the second developer preview 2 weeks ago or 3 weeks ago. And we are planning on, and of course I'm saying planning on because the dates always move, for beta in July, and then hopefully a GA in Q3. That's the idea. You can find the code on Couchbase Labs, Couchbase Spark connector. It's also on the Spark packages. And when we hit GA, we'll have the documentation as part of our official documentations. Right now, it's on the GitHub wiki where I'm updating the documentation as the development proceeds. Now, before we go into a quick demo, here's some actual code so you can get a better feeling of what's going on there. So in Spark, you need to create a configuration, which is called a Spark conf. And there are lots of things you can set there. But in general, what you'll always need is the application name and the master. Now, if you leave the master off, you have to specify it when you deploy it to an application. And this master is kind of special because if you say you set the master to local and the star is just a wildcard here, which means that the Spark will execute in your current JVM, which means that you can develop in your IDE, you can run your computations in your local JVM, you make sure everything is working fine as you expected, and then you can deploy it into a cluster. So if we specify it like that, it's fine for unit tests or for simple demos like we'll do it here. And this is the important part. If you do not specify any params, we'll connect to the default bucket on localhost like we do with the SDKs. But you can say com.couchbase.nodes, and then you pass in the list of nodes to connect to on the cluster. And then what you can also do, you can open more buckets at the same time. So you can say com.couchbase.bucket and then the bucket name, and then the password. And you can specify more buckets. And when you do your data operations, you can specify which bucket you want to use. So an interesting use case is, for example, you have a bucket with lots of data, and you create another bucket, and then you grab data from one bucket, analyze it, merge it, do something with it, and then store the result in another bucket. You can do it with that in one query, basically. So you're not limited to one bucket on one cluster. Now, here's another example. Here we are connecting to the travel sample bucket, and we don't specify a password for that. The next step is we need to create the Spark context. And the Spark context is basically the runtime. Right? We pass in the configuration, and then we can work with the Spark context. So here's an example on how to create an RDD by fetching documents by the unique ID out of Couchbase. So we're doing a key value lookup. On our context, we call parallelize, and we give in a sequence. So this is Scala code. If you've not seen Scala before, I think it's quite easy to grasp, right? So a sequence is like a list, and we pass in the document IDs that we want to load from Spark. And the next method here, which we are extending on the Spark context with the connector, is we call Couchbase get. So we're instructing the Spark connector to load the document from the server. And we give it a document type because the Java SDK supports different document types. You can specify it here by default. The JSON document will return your JSON object, and you can perform the computations. But if you have some raw data or you're storing protobuf or whatever, you can even extract the raw bytes from the document that you get back. We're not limiting you to JSON in any way here. And we're using the map operation to extract the content out of our document. And then we call collect. And the collect is important because maybe it's not obvious here, but all this code is executed on a cluster, right? And by calling collect, you're instructing Spark to say, give me all the data, right? So you don't want to call that until the very end, because you can imagine if you are calling collect on gigabytes of data, it will put it on one machine and then return it to you. But in our case here, it's fine. And then we call for each println, which means that it will print both documents in the end, right? So this is how you in a very declarative way, write your Spark programs. Another thing is you can persist RDDs. So imagine we are creating JSON documents here, and again, we are calling parallelize, which means that we are creating an RDD out of a sequence, right? This is all there is to it. And then we can call save to Couchbase, which will automatically persist the documents into Couchbase, right? So that's all there is to it, which means that, and you can have an infinite number of operations before that, and at the very end, you call save to Couchbase, and it will persist all the documents in your RDD into your Couchbase bucket right away. And what you can also do is if you have pairs, so this is the pair syntax in Scala, so you have a pair of a key and the value. The key is the document ID, and the value here is the JSON object. You can call to Couchbase document, which with the document type, which will try to infer the proper transformation. So it will see, oh, that's actually a pair of a string and a JSON object, and then it will create the JSON document for you under the covers. because handling pairs sometimes is easier in Scala than always manually mapping onto a JSON document. You can do that as well, but you don't have to. So for Spark SQL integration, and we'll see an actual example a little later, you can see that we are calling Couchbase query. So the first one was Couchbase get. This one is Couchbase query. We are passing in the Nickel query. And then again, we are calling collect to grab all the results and print them out. Now, this is the raw way to get data out of Nickel. The much nicer way with Spark SQL is to, this is the SQL context. I'll show you in a bit how to create that. And then we have a Nickel method available there. And we're passing in a filter, which means that since we do not have a concept of tables or collections, the filter, we filter on the type field airline, which means that our data frame here will basically represent all airlines in our bucket. Right? And we can, if we do it like this, it will automatically infer the schema for us, but we can always provide the schema manually with those struct type and struct field commands. You can also manually create a schema for your data frame on top of your data. And then we can perform an operation like this. We can say df.select, sort, and so forth. So this looks very similar to the builder API of Nickel, but it's different. This is part of Spark SQL. This has nothing to do with Couchbase itself. We are performing a Spark SQL operation on top of our data frame. The same API works if you pull in a data frame from Hadoop or from Cassandra or any other system. A final example on DCP streaming. So how can you create a data stream of data coming in from Couchbase? So first, you need to enable DCP here because it's experimental. We already know how to create the configuration here. And you see that we are not specifying any bucket, so we'll use the default bucket in this case. And then we are creating a streaming context. And here we specify basically the batch time, which means that the stream that we're creating will batch the data up in 5-second intervals and then return it into our streaming context here. And the only thing we need to do is we need to call .couchbase stream, and then we call print, which will print everything that's emitted on our stream. And the important part here is you need to start the stream, right? And if you run that code, it keeps running and running and running, and every time a mutation comes in, it will print it out to the command line. But you can imagine adding your data logic right here instead of the print, mapping, doing data analysis or whatsoever. So it's very easy to do those operations. So before we jump into a quick demo, any questions? Yes? Exactly. Exactly. It's running in one JVM. Exactly. Yeah. Yeah. Exactly. It's really meant for unit testing or simple exploration purposes, right? What you do if you're deploying to a production system, you would actually leave the master out completely, and you package your jar up, and then you basically send it to the orchestrator of your Spark cluster, and then, of course, it knows, well, I'm the master, and then it starts distributing it, right? But since it's part of the configuration, all the code you're writing here is not concerned about where it is executed, right? No, it's actually, so it's running either on Mesos or on Yarn. So it's distributing those tasks. And it even has its own scheduler. It also provides its own, but basically then it's running, it's spawning JVM instances where it's dispatching the workers. Yes? Mm-hmm. Yeah, so the question was on the number of buckets to use. Yeah, so the current limit more or less is 10 buckets on a cluster, but that's not related to Spark. It's more a limitation that we basically put on the Couchbase cluster because of resource things. Yeah. Yeah. So the question was, how are partitions created? I didn't cover the concept of Spark partitions in that introduction, but let me briefly mention it. So Spark needs to know how to separate or split up the data into partitions so that it knows how to basically move them onto workers. So what we are doing here, and it's already part of DP2, is that we are actually using the partitions for key value access, right? We know the server has 1024 partitions, and when you do like the Couchbase get, we will hash those IDs internally, and we have the configuration from the server, and then we'll know how many partitions we need to access, and then we'll basically define the partition factor dynamically, and we will hint the preferred location to Spark, right? I didn't cover that here as well because it's pretty, it's meant as an introduction, but what we also do is we provide a location hint. So if you run your Spark workers on the same node where you run your Couchbase data nodes, right, we can avoid shuffle operations because we hint to Spark saying, please fetch this key, but do it from that IP address or that host name, and then Spark will know, okay, the worker is over there. And if it runs on the same machine as the data node with Couchbase, they can basically talk over the local socket, and you avoid shuffling data over the network. And the partitions are figured out the same way, right? It's somewhere between 0 and 1024. Yeah, that's more or less the mapping. The mapping is really the vbuckets to, it depends, it could be less, because if you're requesting only 4 documents, there is no need to fan it to 1024 partitions, right? So it's something, it depends on how many keys you pass in and to how many nodes they actually map, to how many partitions they map. Because it could be that if you request 5 keys, 4 of them could map to one partition and 1 maps to the other one. So we have like parallelism of 2 sending that to Spark. So we are trying to be intelligent, and I'm still working on making that more efficient and so forth, but that's the basic idea. So if I understood the question correctly, are you saying you should run them side by side, or? So the topology is up to you, right? So what the Couchbase connector does, it only provides a hint. It tells Spark, like, you probably want to look there first. If you have a worker running on that node, go look there. But you can either run it on the same nodes, or you can run it completely differently. But then you have shuffle operations going on because we need to talk over the network. But there is no hard requirement to run them side by side. You can mix and match the way you want. If you have really data-intensive operations, right, you probably want to move them closer together to avoid network. But if you only fetch a document here and there, it probably doesn't matter, right? It's more application-specific. All right, then I'll jump into a quick demo. So we are, let me do it here. So here you can see the code that we've seen before. So we're using parallelize to fetch those documents, right? We call Couchbase get to fetch the full documents based on the ID. We extract the content, and then we print it out. And if we run that, so it's doing lots of printing. And you can see that here, if you've used the Java client before, you can see, even if we didn't specifically open a cluster and bucket connection, the connector actually opened it in the background for us and made sure that the proper buckets are open. And then it's executing all those tasks. And here you can see printed on the command line the documents that are part of the driver sample data set, right? It extracted those documents for us. So let's go to another example here. So here we have the nickel query. And again, we have our configuration. We create the Spark context, and then we also create the SQL context and pass it the Spark context in. And here's like a plain old Spark query. So you're creating those RDDs. This is not really part of Spark SQL. But then we can either create our data frame with schema inference. I commented the manual schema creation out here. And then we are printing out the schema, because it's interesting to see what schema the system inferred. And then we are running a query which says, from our airlines, we want to extract the name and the call sign, and we sort by call sign. And then with show, you can actually specify how many records you want to show, which is interesting, especially for quick debugging, does my query work, and so forth. So if we run that, wrong file, of course. Again, it does lots of info output. So the first one was the raw nickel query we specified on this one. Select star from travel sample limit 10. So we get 10 rows, like the real JSON objects out of our row here. But the more interesting stuff starts down here. So we said, print the schema of our data frame. And this is the schema it inferred from the system, which are exactly those fields we have in our system. So if you have a pretty rigid schema, the automatic schema inference works pretty well. And what the data frame does at this point, because it does the lookup, if you are requesting, for example, like name 1 here, and you run it, it will fail saying there is no field name 1 on your schema, right? So it's more like table-oriented in a SQL fashion. And then if we scroll down here, our actual query, we select name and call sign, and we sorted it by the call sign, right? So that's basically part of our data set. So you can see really like with 4 lines or 5 lines of code, of actual code, you can very quickly perform data analysis on the system. Now let me do a final one. I've created another bucket on my system. It's called Twitter, and we are doing some Spark streaming. There is a Spark streaming Twitter module which allows you to feed data out of a Twitter stream, and I set the consumer key and secrets and tokens as part of my run configuration, because that's not, I don't want to show them on the slides here, but they're just set as a property. The important part is here. So every 2 seconds we get data emitted, and with the Twitter utils we create this D-stream, and then we have our hashtags, and for every RDD that is created as part of our hashtag, we call the map operation, and we map from the status, and the status is, going here. So the status is really an object that is returned from Twitter 4J. So you see there's get geolocation, created that, contributors. It's like whatever metadata is available from Twitter for each status update. Now in our case, we are only interested in the ID, and we are interested in the text, right? So we create a document for each status that's incoming. We create a document. The document ID is the ID that is provided here, and then we create a JSON object. The text is the text, right? And then we start, and then we await termination. And if we run that, and then go to our UI here. So there is this Twitter bucket, and you can see that it starts to oscillate because we have this 2-second batch interval that the Spark streaming waits to emit data. So it will every 2 seconds it emits data in here, and then you can basically look here, and you can see that all those tweets, I didn't filter anything, I just as demo purpose. You can see that it did feed all the data. I want chicken wings and yeah, whatever. So, but you can see that it's very easy to use Couchbase also as a fire hose to feed data from a Twitter stream or any other Spark stream into Couchbase with just a few lines of code. And there, I think it would be just keep going and going and going, right? So, and there you can see it's constantly updating the stream and logging info messages and so forth. So with that, I think we are right on time. There's probably beer and food outside there, so I don't want to hold you up any longer. I'll be around the whole evening and the full day tomorrow. Thank you very much for attending, and enjoy the rest of the conference.